You know what is the strangest thing about the night sky? It is not the stars. It is not the galaxies. It is not the black holes or the nebulae or the supernovae. The strangest thing about the night sky is the silence. Go outside tonight, look up, and just listen. Not with your ears, but with your mind. You are looking at a universe that is 13.8 billion years old. You are looking at hundreds of billions of galaxies, each containing hundreds of billions of stars, each of those stars potentially orbited by planets, many of those planets sitting in the perfect zone where water can exist as a liquid, where temperatures are just right, where the chemistry of life as we know it could unfold. You are looking at a cosmos so incomprehensibly vast that the human brain literally cannot process it. And in all of that space, across all of that time, with all of those possibilities, we have found exactly zero evidence of anyone else. Nothing, not a signal, not a whisper, not a footprint, not a single artifact, not one undeniable proof that any other intelligent being has ever existed anywhere in this universe besides us. And that silence, that deafening, screaming, unbearable silence, might be the most terrifying thing humanity has ever encountered. Welcome back, and today we are going on a journey. But I have to warn you, this is not a casual trip. This is not one of those videos where we scratch the surface and move on. No, today we are going deep. We are going to the very bottom of one of the most disturbing questions in all of science, all of philosophy, and arguably all of human existence. By the time this video ends, I promise you, you will not look at the night sky the same way. You will not think about your place in this universe the same way. Some of what we discuss today will fascinate you. Some of it will fill you with wonder. And some of it, honestly, some of it might genuinely frighten you. Because today we are going to talk about why the universe is quiet. And we are going to explore every possible explanation for that silence, from the mathematical frameworks that predict millions of civilizations should exist, to the chilling theories that suggest something is hunting them, or that they are all hiding, or that they all destroyed themselves, or that we are living inside a construct built by something we cannot even begin to comprehend. Here is what we are going to cover. First, we are going to understand the sheer scale of this universe, the numbers, the distances, the timescales, because you cannot appreciate the paradox without first appreciating the stage on which it plays out. Then we are going to meet a man named Enrico Fermi, and we are going to understand why a single question he asked over lunch in 1950 became one of the most important questions in the history of science. We are going to break down the Drake equation, humanity's attempt to mathematically calculate how many alien civilizations should exist. Then we are going to confront the paradox head-on, and we are going to walk through every major hypothesis, every theory, every terrifying possibility that scientists and thinkers have proposed to explain the silence. The rare earth hypothesis, the great filter, the dark forest theory, the berserker hypothesis, the zoo hypothesis, the estivation hypothesis, the planetarium hypothesis, the self-destruction hypothesis, the transcendence hypothesis, and more. We are going to look at the actual evidence, the WOW signal of 1977, the strange dimming of Tabby's star, the latest discoveries from the James Webb Space Telescope, and we are going to examine what SETI has been doing for 60 years, and why they have found nothing. And then, at the very end, we are going to ask the question that matters most. What does the silence mean for us? For humanity? Right now? What does it mean for our future? Are we early? Are we late? Are we alone? Or are we in danger? So before we go any further, if this is your first time here, this is what we do. We take the biggest, deepest, most mind-bending questions about our universe, and we explore them from every angle, with every detail, with the curiosity and depth they deserve. If that excites you, hit the subscribe button right now, ring that notification bell, and drop a comment telling me what you think. Do you believe we are alone in this universe? Or do you think something else is going on? I read every single comment, and I am genuinely curious what you think. Because by the end of this video, your answer to that question might completely change. Let us begin. Let us start with the stage. The universe. And let me try to give you a sense of just how absurdly, incomprehensibly, almost offensively large it is, because the Fermi paradox does not hit you until you truly internalize the scale. The observable universe, and I want to emphasize that word observable because the actual universe might be infinitely larger, the part we can see is about 93 billion light years in diameter. A light year is the distance light travels in 1 year, and light moves at roughly 300,000 kilometers per second. So in 1 year, light covers about 9.5 trillion kilometers. Now multiply that by 93 billion. That is the diameter of the part of the universe we can observe. It is a number so large that writing it out would take up most of this screen. And this is just the part we can see. The actual universe, according to some models of cosmic inflation, might be 10 to the power of 20, 3 times larger than the observable universe. That number is so big that calling it astronomical is almost an insult to the word. Within this observable universe, there are approximately 2 trillion galaxies. That number was revised upwards significantly by studies using Hubble Space Telescope data. 2 trillion. 2 followed by 12 zeros. Each of these galaxies contains, on average, somewhere between 100 billion and 400 billion stars. Our own galaxy, the Milky Way, contains roughly 200 to 400 billion stars. And the Milky Way is actually a medium to large galaxy. There are galaxies far larger, like IC 1101, which contains roughly 100 trillion stars. So let us do some rough math. 2 trillion galaxies times, let us say, 200 billion stars per galaxy on average. That gives us something like 4 times 10 to the 23 stars. That is 400 sextillion stars. To put that in perspective, there are estimated to be about 7.5 times 10 to the 18 grains of sand on all the beaches of Earth. That means there are roughly 50,000 stars for every single grain of sand on every beach on the entire planet. Now here is where it gets really interesting. We used to think that planets were rare. Just a few decades ago, many astronomers believed that our solar system might be unusual, that having planets orbiting a star was the exception rather than the rule. We were wrong. Spectacularly wrong. The Kepler Space Telescope, launched by NASA in 2009, changed everything. By monitoring the brightness of over 150,000 stars simultaneously for years, looking for the tiny dips in light that occur when a planet passes in front of its star, Kepler found that planets are everywhere. Not just common, everywhere. The data shows that on average, every star in the Milky Way has at least one planet. Many have multiple planets. Some have entire solar systems. The galaxy contains at least as many planets as stars, and probably far more. Conservative estimates suggest there are at least 100 billion planets in the Milky Way alone. Some estimates go as high as 400 billion. But not all planets are equal when it comes to life. What we really want to know is how many planets exist in the so-called habitable zone, sometimes called the Goldilocks zone, the region around a star where temperatures are just right for liquid water to exist on a planet's surface. Not too hot, not too cold. And here again, the numbers are staggering. Based on Kepler data and subsequent analyses, astronomers estimate that there are at least 11 billion Earth-sized planets orbiting in the habitable zones of Sun, like stars in the Milky Way. If you include planets around red dwarf stars, which are far more numerous than Sun-like stars, that number jumps to about 40 billion potentially habitable Earth-sized worlds. 40 billion. In our galaxy alone. And remember, there are 2 trillion galaxies in the observable universe. So when we talk about the potential for life, we are not talking about a handful of candidates. We are talking about numbers so vast that even the most conservative estimates yield millions, billions, potentially trillions of worlds where life could, in principle, arise. But there is another factor that makes this even more compelling, and that factor is time. The universe is 13.8 billion years old. Our sun, our star, is about 4.6 billion years old. That means the universe existed for over 9 billion years before our sun even formed. During those 9 billion years, countless other stars were born, lived, and died. Many stars that formed in the early universe were similar to our sun. Some were even more hospitable to the development of life. And crucially, many of these stars and their planets are billions of years older than Earth. Think about what that means. Life on Earth appeared remarkably quickly, geologically speaking. The oldest evidence of life on Earth dates to about 3.8 to 4 billion years ago, meaning life appeared within the first 500 million to 700 million years of Earth's existence. Some evidence suggests it might have appeared even earlier. The point is, life did not take long to get started on Earth. If conditions on other Earth-like planets are similar, and if the chemistry of life is not extraordinarily rare, then life could have arisen on planets around older stars billions of years before it arose on Earth. A civilization that had even a 1 million year head start on us, just 1 million years, would be so far beyond our comprehension that we might not even recognize it as a civilization. Think about where humanity was 1 million years ago. We were barely using stone tools. We had not yet controlled fire reliably. Now think about where we are today, with our smartphones and our space stations and our artificial intelligence. Now extrapolate 1 million more years into the future. Or 10 million. Or 100 million. Or a billion. A civilization with a billion-year head start on us is so far beyond our imagination that trying to understand them would be like an ant trying to understand quantum physics. It would not just be difficult, it would be fundamentally impossible. And yet, here we are. A young species on a young planet around a young star, looking up at a cosmos filled with billions of older, equally suitable worlds, and finding absolutely nothing. No signals, no megastructures, no evidence of galactic colonization, no probes, no artifacts, nothing. That is the setup. That is why the silence is so disturbing. It is not that we have not found aliens. It is that we should have found them by now, many times over, and we have not. The universe is screaming with potential and whispering with reality. Now let me tell you about the moment this contradiction crystallized into one of science's greatest mysteries. The year was 1950. The place was Los Alamos National Laboratory in New Mexico, one of the most secretive and intellectually concentrated places on Earth. This was the birthplace of the atomic bomb, the place where the greatest minds of the 20th century had been assembled to crack open the secrets of nuclear physics. And among those minds was one of the greatest physicists who ever lived, a man named Enrico Fermi. To understand why Fermi's question carried so much weight, you need to understand who Fermi was. Enrico Fermi was born in Rome, Italy, in 1901. By the time he was in his mid-20s, he had already made fundamental contributions to quantum theory and nuclear physics. He won the Nobel Prize in Physics in 1938 for his work on induced radioactivity. He was one of the architects of the nuclear age. He designed and built Chicago Pile 1, the world's first artificial nuclear reactor, underneath the stands of a football stadium at the University of Chicago in 1942. This was a pivotal moment in the Manhattan Project, the secret program that would produce the atomic bombs dropped on Hiroshima and Nagasaki. But Fermi was known for something beyond his technical brilliance. He was famous for what became known as Fermi problems, or Fermi questions. These were seemingly impossible estimation problems that Fermi could solve, or at least approximate, through pure logical reasoning and back-of-the-envelope calculations. How many piano tuners are there in Chicago? How far can a crow fly without stopping? How many atoms of Caesar's last breath do you inhale with each lungful of air? Fermi had an uncanny ability to take impossibly vague questions and arrive at surprisingly accurate answers through systematic logical reasoning. So when Fermi turned his attention to a question, even a casual one over lunch, the scientific community paid attention. In the summer of 1950, Fermi was at Los Alamos for a consultation visit. One day, he was walking to the Fuller Lodge for lunch with 3 colleagues, fellow physicists Edward Teller, Emil Konopinski, and Herbert York. As they walked, their conversation turned to recent reports of flying saucers in the newspapers. There had been a cartoon in the New Yorker depicting aliens. They discussed the feasibility of faster-than-light travel and whether flying saucers could be real. The tone was casual, joking, playful. They were some of the smartest people alive, riffing on science fiction over lunch. They sat down to eat. The conversation drifted to other topics, work, politics, whatever scientists talk about over lunch. And then, seemingly out of nowhere, Fermi suddenly exclaimed what has been variously remembered by those present as, "Where is everybody?" Or "Do you ever wonder where everybody is?" Or "But, where is everybody?" According to Edward Teller, the result of his question was general laughter, because despite the question coming completely out of the blue, everyone at the table immediately understood that Fermi was talking about extraterrestrial civilizations. The laughter faded quickly, because the question was not really funny. It was deeply serious. According to Herbert York, Fermi then followed up with a rapid series of calculations, right there at the lunch table. He estimated the probability of Earth-like planets, the probability of life arising on such planets, the probability of intelligent life evolving, the likely development and duration of technological civilizations, and he concluded, based on these back-of-the-envelope calculations, that Earth ought to have been visited long ago, and many times over. But it had not been, and that was the paradox. Now, I want to be clear about something. Fermi himself never published a formal paper about this paradox. He did not even use the word paradox. The term Fermi paradox was actually coined later, in 1977, by David Stevenson, and the paradox was formally developed and rigorously analysed by other scientists, most notably Michael Hart in 1975 and Frank Tipler in 1980. But the seed was planted that day at lunch in Los Alamos, a simple question, where is everybody, that continues to haunt humanity to this day. Let me now lay out the paradox in its most rigorous form, because I want you to feel the full weight of it. The argument goes like this. The Milky Way galaxy contains between 200 and 400 billion stars. A significant fraction of these stars are similar to our Sun. Many of these Sun-like stars are billions of years older than our Sun. Based on what we know from exoplanet surveys, a substantial percentage of these stars have planets, and many of those planets orbit in habitable zones. If even a small fraction of these habitable planets develop life, and if even a small fraction of that life eventually becomes intelligent and technological, then the galaxy should contain a significant number of advanced civilizations. Some of these civilizations would be millions or billions of years older than ours. Now here is the crucial step. Even if interstellar travel is extremely slow, even if no civilization ever exceeds 1% of the speed of light, mathematical models show that a single motivated civilization could colonize the entire Milky Way galaxy in as little as 1 million to 10 million years. That sounds like a long time, but it is a cosmic blink. The galaxy is over 13 billion years old. 10 million years is less than 1/10 of 1% of the galaxy's age. Self-replicating probes, sometimes called von Neumann probes after the mathematician John von Neumann, who first described the concept of self-replicating machines, could theoretically explore and catalogue every star system in the galaxy in an even shorter time frame, perhaps just a few 100,000 years. So if even one civilization out of potentially millions decided to expand across the galaxy at any point in the last several billion years, the galaxy should be colonized by now. We should see evidence. Everywhere, but we do not. This is the paradox. Not a minor puzzle. not a cute riddle, a fundamental contradiction between what our best science tells us should be true and what we actually observe. And the resolution of this contradiction could be one of the most important discoveries or one of the most terrifying realizations in human history. Now, before we dive into the possible explanations, I want to tell you about humanity's first formal attempt to put numbers on this mystery, because it is brilliant and it reveals both the promise and the profound ignorance that characterize our search for cosmic company. In 1961, just 11 years after Fermi's legendary lunch question, a young astronomer named Frank Drake organized a small conference at the Green Bank Observatory in West Virginia. The purpose was simple but ambitious: to bring together some of the best scientific minds of the era to seriously discuss the possibility of detecting extraterrestrial intelligence. Only 10 people attended, but among them were some of the most brilliant scientists of the 20th century, including a young astronomer named Carl Sagan, who would later become the most famous science communicator in history. To give structure to the discussion, Drake did something elegant. He wrote a single equation on the blackboard. This equation, now known as the Drake equation, was not meant to give a precise answer. It was meant to organize our ignorance, to break down the overwhelming question of how many civilizations exist into a series of smaller, more manageable questions that could, in principle, be answered through observation and research. The equation looks like this: n equals r star times fp times ne times fl times fi times fc times l. Each variable represents a different factor in the chain, from star formation to communicating civilizations. Let me walk you through each one, because understanding this equation is essential to understanding why the silence is so paradoxical. R star is the rate of star formation in our galaxy, the number of new stars born per year. This is actually the variable we know best. Observations tell us the Milky Way forms roughly 1.5 to 3 new stars per year. It is not a huge number, but the galaxy has been doing this for billions of years, so the cumulative total is enormous. Fp is the fraction of those stars that have planetary systems. Just a few decades ago, this was a complete unknown. We had only confirmed planets in our own solar system. Then came the exoplanet revolution. Starting with the first confirmed exoplanet discovery in 1995 and exploding with the Kepler mission, we now know that planets are ubiquitous. The current best estimate for Fp is roughly 1, or very close to it. Essentially, every star has at least one planet. Some have many more. Ne is the average number of planets per star that could potentially support life. This includes planets in the habitable zone, as well as moons with potential subsurface oceans. Based on Kepler data, estimates for Ne range from about 0.2 to 0.5 for Sun-like stars. This means roughly 1 in 5 Sun-like stars has an Earth-sized planet in its habitable zone. Now here is where the equation gets uncertain, and this is critically important. Fl is the fraction of potentially habitable planets where life actually arises. We have exactly one data point: Earth. Life appeared on Earth relatively quickly once conditions were suitable, which some interpret as evidence that abiogenesis, the emergence of life from non-living chemistry, is relatively easy when the conditions are right, but we simply do not know. F-full could be close to 1, meaning life arises almost inevitably given the right conditions. Or it could be astronomically small, meaning life on Earth was a 1 in a trillion fluke. Fi is the fraction of life bearing planets where intelligent life evolves. Again, we have one data point. Life on Earth existed for roughly 3.5 billion years before anything resembling human-level intelligence appeared. Many biologists argue that intelligence is not an inevitable outcome of evolution. Evolution does not have a direction. It does not climb toward intelligence like climbing a ladder. Intelligence is just one of many possible survival strategies, and it happened to work for one particular lineage of primates on one particular planet. On the other hand, convergent evolution, the phenomenon where similar traits evolve independently in unrelated species, has produced intelligence like traits multiple times on Earth. Octopuses, crows, dolphins, elephants all demonstrate remarkable cognitive abilities. So maybe the emergence of some form of intelligence is more likely than we think. We simply do not know. FC is the fraction of intelligent civilizations that develop technology capable of producing detectable signals, things like radio transmissions, laser beacons, or large-scale engineering projects. This is another deep unknown. Could there be intelligent civilizations that never develop technology? Absolutely. Dolphins are remarkably intelligent, but will never build radio telescopes, because they live in water and have no hands. What fraction of intelligent species go on to become technological civilizations? We have no idea. And then there is L, possibly the most important and most uncertain variable of all. L is the length of time that a technological civilization remains detectable, the length of time it transmits signals into space. This could be as short as a few hundred years if civilizations tend to destroy themselves shortly after developing powerful technology. Think nuclear weapons, artificial intelligence, climate change, engineered pandemics. Or L could be millions or billions of years if civilizations find ways to survive and sustain themselves over cosmic timescales. The value of L changes everything. If L is small, the galaxy could be full of civilizations that bloom and die like mayflies, never overlapping in time. If L is large, the galaxy should be a bustling metropolis of ancient, enduring civilizations. When the original Green Bank attendees plugged in their best guesses for each variable, they arrived at estimates for N, the number of communicating civilizations in the Milky Way, ranging from about 1,000 to 100 million. Even the conservative end of that range is extraordinary. 1,000 civilizations in our galaxy alone, each potentially broadcasting signals, each potentially building megastructures, each potentially colonizing star systems. But here is the sobering counterpoint. In 2018, a team of researchers led by Anders Sandberg, Eric Drexler, and Toby Ord at the Future of Humanity Institute at Oxford published a rigorous Bayesian analysis of the Drake equation. Instead of plugging in single best guesses for each variable, they assigned probability distributions to account for our genuine uncertainty. When they did this, they found something startling. There is a 39 to 85% probability that we are alone in the observable universe. Not just alone in the galaxy, alone in the entire observable universe. The reason is that the uncertainties in the Drake equation are so large, spanning many orders of magnitude for variables like FL and FI, that when you properly account for that uncertainty, the probability distribution for N includes 0. In other words, our current knowledge is consistent with us being completely alone. This does not mean we are alone. It means we genuinely do not know. And that uncertainty itself is a kind of answer, a humbling reminder that for all our telescopes and space probes and mathematical frameworks, we still have no idea whether anyone else is out there. But the silence continues. And the silence demands explanation. Now we arrive at the heart of this video. The explanations. The hypotheses, the theories that scientists, philosophers and thinkers have proposed to resolve the Fermi paradox. And I want to take you through each one in depth, because each one reveals something profound about the nature of the universe, the nature of life, and the nature of intelligence itself. Broadly speaking, the proposed solutions fall into several categories. Some argue that intelligent life is far rarer than we think. Some argue that intelligent life exists but is undetectable for various reasons. Some argue that intelligent life exists but deliberately avoids contact. Some argue that there is a barrier, a filter, that prevents civilizations from reaching a detectable or expansionist stage. And some argue that our fundamental assumptions about the nature of reality are wrong. Let us begin with what might be the simplest explanation, and work our way toward the more disturbing ones. The first major hypothesis is the rare Earth hypothesis, and it argues that the conditions required for complex life are so extraordinarily specific and so dependent on an improbable chain of cosmic coincidences that Earth might be genuinely unique, or at least extraordinarily rare, in the entire galaxy, or even the entire universe. This hypothesis was most famously articulated by paleontologist Peter Ward and astronomer Donald Brownlee in their 2000 book Rare Earth: Why Complex Life is Uncommon in the Universe. Their argument is not that microbial life is rare. Simple, single-celled life might be common throughout the cosmos. Their argument is that the leap from simple microbial life to complex multicellular life, and especially to intelligent technological life, requires such a specific and unlikely combination of factors that it might almost never happen. Consider the chain of requirements. First, you need the right kind of galaxy. Not all galaxies are hospitable to life. Elliptical galaxies, which make up a large fraction of all galaxies, tend to have older stellar populations, higher rates of stellar encounters, and more radiation. The Milky Way is a spiral galaxy, which might be more conducive to the stable conditions life requires. Then you need the right location within that galaxy. Too close to the galactic center, and you are bathed in lethal radiation from the supermassive black hole, nearby supernovae, and gamma-ray bursts. Too far out, and there are not enough heavy elements, because heavier elements are produced in the cores of massive stars and distributed by supernovae, and these are more common toward the galactic center. Earth sits in what some astronomers call the galactic habitable zone, a relatively narrow band neither too close nor too far from the center. You need the right kind of star. Our Sun is a G-type main sequence star, sometimes called a yellow dwarf. It has several properties that might be crucial for life. It is relatively stable, meaning it does not produce devastating flares or vary dramatically in luminosity. It has a long lifetime, about 10 billion years, giving life plenty of time to evolve, and it sits in a relatively quiet neighborhood of the galaxy. Many other types of stars are less hospitable. Red dwarfs, the most common type of star, tend to be flare stars that periodically blast their planets with lethal radiation. They are also so dim that habitable zone planets must orbit very close, becoming tidally locked with one face permanently facing the star and the other in eternal darkness. You need the right kind of planet. Earth is a rocky planet with a solid surface, a strong magnetic field generated by a molten iron core, a moderate axial tilt that creates stable seasons, a rotation rate that creates a reasonable day-night cycle, and enough mass to hold on to a substantial atmosphere without becoming a gas giant. Earth also has plate tectonics, which is crucial for recycling carbon and maintaining a stable climate over billions of years through the carbon-silicate cycle. Without plate tectonics, Earth might have suffered the same fate as Venus, a runaway greenhouse effect that turned it into a hellish furnace. You need water. Lots of it. In liquid form. Earth has oceans that cover about 70% of its surface. Where did all that water come from? The leading hypothesis is that it was delivered by asteroids and comets during the late heavy bombardment period. The amount and timing of water delivery to Earth might be a critical and improbable factor. You need a protective magnetic field. Earth's magnetic field is generated by convection currents in its liquid iron outer core. This magnetic field creates a magnetosphere that shields the surface from the solar wind and cosmic radiation. Without it, the solar wind would strip away Earth's atmosphere, much as it stripped away Mars's atmosphere when Mars's magnetic field died billions of years ago. You need a large moon. Earth's moon is unusually large relative to its host planet. It is thought to have formed from a giant impact between the proto-Earth and a Mars-sized body called Theia, roughly 4.5 billion years ago. The moon stabilizes Earth's axial tilt, preventing chaotic variations that would cause extreme climate swings. Without the moon, Earth's axial tilt could vary wildly over millions of years. creating conditions hostile to the long-term stability that complex life requires. You need giant planets in the right orbits. Jupiter and Saturn, with their enormous gravitational fields, act as cosmic vacuum cleaners, deflecting or absorbing many of the comets and asteroids that would otherwise bombard the inner solar system. Without Jupiter, the rate of catastrophic impacts on Earth would be much higher, potentially preventing complex life from ever getting a foothold. Though some models suggest Jupiter also redirects some objects toward the inner solar system, the net effect is generally thought to be protective. You need the right chemistry. Life as we know it is based on carbon, which is uniquely versatile in its ability to form complex molecules. Carbon can form 4 covalent bonds, allowing it to create the long chains and complex structures necessary for the molecules of life, proteins, nucleic acids, lipids, carbohydrates. You also need liquid water as a solvent, an energy source, and a collection of other elements in the right proportions. While carbon and water are common in the universe, the specific conditions needed for them to interact in just the right way to produce self-replicating molecules might be exceedingly rare. And then there are the evolutionary contingencies. Even if you get all the planetary conditions right, the history of life on Earth is littered with events that seem singular and unpredictable. The emergence of photosynthesis, which produced the oxygen that made complex life possible, happened once. The development of eukaryotic cells, complex cells with nuclei, appears to have happened through a freak merger between an archaeal cell and a bacterium, what biologists call endosymbiosis. This event, as far as we can tell, happened exactly once in the entire history of life on Earth. If it is truly that improbable, then most planets with life might be forever stuck at the microbial stage. The Cambrian explosion, roughly 540 million years ago, when complex multicellular animal life suddenly diversified into an enormous array of forms, appears to have been triggered by a specific combination of environmental factors, including rising oxygen levels, the breakup of a supercontinent, and other conditions that might not repeat on other worlds. And then there are the mass extinctions. 5 major mass extinctions have punctuated the history of life on Earth. The most famous, the asteroid impact that wiped out the non-avian dinosaurs 66 million years ago, actually cleared the way for mammals to diversify and eventually produce primates, which eventually produced us. Without that asteroid, intelligent life on Earth might never have evolved. What if that impact was a 1 in a million event? What if on most planets, the dominant species never get knocked out of their ecological niche, preventing other lineages from diversifying? The rare Earth hypothesis essentially argues that when you multiply all these probabilities together, the fraction of planets that satisfy all the requirements for complex intelligent life is so astronomically small that we might be the only such planet in the observable universe. Not because any single requirement is impossibly unlikely, but because the chain of requirements is so long that the cumulative probability approaches 0. This is a sobering thought. It suggests that the silence is not evidence of something sinister. It is simply the reflection of a profound cosmic loneliness. We are alone not because something killed everyone else, but because no one else ever existed. But there are strong counter-arguments to the rare Earth hypothesis. Many scientists point out that it assumes the specific pathway that led to intelligent life on Earth is the only possible pathway. Life elsewhere might be based on entirely different chemistry, different solvents, different energy sources. Silicon-based life, ammonia-based life, life in the atmospheres of gas giants, life in subsurface oceans heated by tidal forces rather than starlight. The universe might be far more creative than our single example suggests. Furthermore, the rare Earth hypothesis suffers from a fundamental statistical problem. We are drawing conclusions about cosmic probabilities from a sample size of 1. It is like finding a single red marble in a bag and concluding that all marbles in all bags everywhere are red. Our sample is hopelessly biased by the fact that we can only observe our own existence. Still, The rare Earth hypothesis remains one of the most scientifically grounded explanations for the silence, and it forces us to confront the possibility that the cosmos might be a very lonely place. But let us assume, for the sake of argument, that life is not that rare. Let us assume that the Drake equation's optimistic estimates are closer to the truth, that there are thousands or millions of planets in our galaxy where life has arisen. This brings us to what is arguably the most important and most terrifying concept in all of astrobiology: the Great Filter. This concept was introduced by economist and futurist Robin Hanson in 1996, and it has haunted the scientific community ever since. The idea is elegant and disturbing in equal measure. Hanson's argument starts from the observation we have already established: the galaxy appears empty. No alien civilizations. No evidence of galactic colonization. No signals. Nothing, given the age of the galaxy and the number of habitable planets. Something must be preventing the emergence of galaxy-spanning civilizations. Something in the long chain of events between a barren planet and a civilization capable of colonizing the stars must be incredibly unlikely, a nearly impossible barrier that almost nothing can get past. Hanson calls this barrier the Great Filter. Think of it this way. Between dead rock and a civilization that has spread across the stars, there are many steps. The formation of a suitable planet, the emergence of life from non-living chemistry, the development of simple cells, the leap from simple prokaryotic cells to complex eukaryotic cells, the evolution of multicellularity, the development of sexual reproduction, the emergence of intelligence, the development of technology, the development of spacefaring capability, the actual colonization of other star systems, and sustained long-term survival as a spacefaring civilization. Each of these steps has some probability of occurring. The Great Filter hypothesis says that at least one of these steps must be almost impossibly unlikely. It must be so improbable that out of the billions of potentially habitable planets in our galaxy, essentially none make it through. The terrifying question is, where is the Great Filter? Is it behind us or ahead of us? If the Great Filter is behind us, that means one or more of the steps we have already passed through was the nearly impossible one. Maybe the emergence of life itself is the filter, so improbable that Earth is one of the only places it ever happened. Or maybe the development of eukaryotic cells is the filter, that freak endosymbiosis event that happened only once in 4 billion years of life on Earth. Or maybe the evolution of intelligence is the filter, requiring such a specific and improbable chain of evolutionary events that it almost never happens. If the Great Filter is behind us, that is actually wonderful news for humanity. It means we have already passed through the hardest part. The silence of the universe is simply because almost no other planet ever made it as far as we have. We are the winners of a cosmic lottery, and the road ahead, while challenging, does not contain an impassable barrier. But if the Great Filter is ahead of us, then we are in deep trouble. If the Great Filter is ahead of us, it means that the steps we have already passed through, the emergence of life, the development of complex cells, the evolution of intelligence, are all relatively common. Many civilizations have made it to where we are now. But then something happens. Something that almost every civilization encounters at roughly our stage of development. Something that stops them cold. Something that prevents them from ever becoming a spacefaring, galaxy-colonizing civilization. What could that something be? The most obvious candidate is self-destruction. A civilization develops nuclear weapons and wipes itself out. Or it develops artificial intelligence that turns against it. Or it exhausts its planet's resources and collapses. Or it triggers catastrophic climate change that renders its world uninhabitable. Or it creates a pandemic through biological engineering. Or it falls into a permanent state of technological stagnation and cultural decline. Think about humanity right now. We have nuclear weapons capable of ending civilization. We are developing artificial intelligence that some of our smartest thinkers including Stephen Hawking and Elon Musk, have warned could pose an existential threat. We are changing our planet's climate in ways that could have catastrophic consequences. We are developing genetic engineering tools that could create devastating biological agents. We are depleting natural resources at an unsustainable rate. We have had nuclear weapons for less than a century, and we have already come terrifyingly close to using them in an all-out war multiple times. The Cuban Missile Crisis. The 1983 Soviet nuclear false alarm incident. Numerous other close calls that most people have never heard of. Is it possible that this is the pattern? That every civilization, when it reaches the point of having the technology to destroy itself, does exactly that? That the window between developing powerful technology and destroying yourself with that technology is so narrow that almost nobody makes it through. This is the nightmare scenario of the Great Filter. That the universe is silent not because life is rare, but because civilizations are common and they all destroy themselves. That the quiet night sky is not a reflection of cosmic loneliness, but a vast graveyard of civilizations that burned bright and then burned out. And here is what makes this even more disturbing. If we ever discover evidence of simple life elsewhere in our solar system, on Mars, on Europa, on Enceladus, that would normally be celebrated as one of the greatest scientific discoveries in history. And it would be. But it would also be terrifying. Because it would mean that the early steps of the Great Filter, the emergence of life, the development of cells, are not that improbable. It would push the Great Filter later in the sequence, closer to our current stage or beyond it. It would increase the probability that the Great Filter is ahead of us, not behind us. As philosopher Nick Bostrom put it in a famous essay, the finding of even simple life on Mars would be bad news. The more complex the life we find, the worse the news. If we found fossil evidence of multicellular life on Mars, it would be devastating for our long-term prospects, because it would suggest that the steps up to multicellular life are easy, and therefore the impossibly hard step must come later, perhaps at exactly the stage we are at now. This is why some scientists have said that the best possible outcome of our search for extraterrestrial life is that we find nothing. A completely sterile Mars, a lifeless Europa, a dead Enceladus. That would be the most hopeful scenario. Because it would suggest that the Great Filter is behind us, that the emergence of life itself is the nearly impossible step, and that we are one of the extremely rare planets that made it through. The Great Filter concept reframes the entire Fermi paradox from an abstract intellectual puzzle into an urgent existential question. It is not just about whether aliens exist, it is about whether we will survive. The silence of the universe might be a warning, a cosmic cautionary tale written in the language of absence. But the Great Filter, as powerful as it is just one possible explanation for the silence. Let me take you deeper into the darkness with what many consider the most chilling hypothesis of all, the dark forest theory. This idea, which gained widespread public attention through Lou Sixon's masterful science fiction novel The Dark Forest, the second book in the Remembrance of Earth's Past trilogy, is a game-theoretic argument for why the universe is silent. And once you understand it, you might wish you had never looked at the stars. The theory rests on two axioms that most scientists would agree are reasonable. Axiom 1. Survival is the primary need of civilization. Every civilization, regardless of its biology, its culture, its values, its technology, has one fundamental imperative: to survive. This is not a moral judgment. It is simply a statement about what it means to be a civilization. A civilization that does not prioritize its own survival will not exist for long. Axiom 2. Civilizations continuously grow and expand, but the total matter and energy in the universe is finite. Resources are limited. Living space is limited. Energy is limited. As civilizations grow, they require more resources, and those resources must come from somewhere. Now add two crucial conditions. Condition 1. There is no way to know for certain whether another civilization is hostile or peaceful. Communication across the vast distances of space is slow, taking years, decades, centuries, or millennia. You cannot have a real-time conversation. You cannot look into their eyes. You cannot read their body language. You cannot examine their history. You know nothing about them except that they exist. And they know nothing about you except that you exist. Condition 2. Any civilization could potentially destroy any other civilization if it wished, especially with the technological advantages that even a few centuries of additional development would provide. A civilization even slightly more advanced than another could, in principle, wipe it out. Now consider the logic that emerges from these axioms and conditions. You are a civilization. You detect a signal from another civilization. You have no idea whether they are peaceful or hostile. You have two options. You can try to communicate with them, establish a dialogue, perhaps even cooperate, or you can remain silent. If you try to communicate, several things might happen. They might be friendly, and you might form a beneficial relationship, but they might be hostile, and now they know where you are. Even if they seem friendly, you can never be sure they will not become hostile in the future. Even if they are peaceful now, their descendants might not be. Even if they are genuinely benevolent, there is no guarantee that a third civilization will not intercept your communications and decide to destroy both of you. Now add the concept of the chain of suspicion. Even if you believe they are peaceful, you cannot know whether they believe you are peaceful. Even if they believe you are peaceful, they cannot know whether you believe they believe you are peaceful. This chain of mutual uncertainty extends infinitely, and it can never be fully resolved across the vast distances and time delays of interstellar space. The logical conclusion, the only rational strategy in a universe governed by these axioms, is to remain silent. And if you detect another civilization, the safest strategy is to destroy them before they can destroy you, because the risk of annihilation always outweighs the potential benefit of contact, especially when you cannot verify the other party's intentions, and the consequences of being wrong are extinction. This is the dark forest theory. The universe is like a dark forest at night. Every civilization is a silent hunter, creeping through the trees, trying not to make a sound. Because in this forest, the moment you reveal your position, you become a target. The moment you shout into the darkness, something in the darkness might come for you. And the silence we observe is not evidence that we are alone. It is evidence that everyone else is hiding. They are out there, all around us, in vast numbers. But they are all perfectly, deliberately, terrifyingly silent because they understand the nature of the forest. They understand that making noise is a death sentence. What makes this theory so chilling is that it does not require any civilization to be evil. It does not require malice. It does not even require aggression. It emerges purely from logic, from the rational calculus of survival in a universe with limited resources, vast distances, and irreducible uncertainty. Even a civilization of pacifist philosophers would, according to this logic, remain silent and potentially strike first, because the alternative is to risk extinction based on faith in the benevolence of an unknown entity. The dark forest theory has a disturbing implication for humanity. We have not been silent. We have been incredibly loud. For over a century, we have been broadcasting radio signals into space. Television broadcasts, radar pulses, military communications, all of these have been leaking into the cosmos at the speed of light, creating an expanding bubble of electromagnetic noise roughly 100 light-years in radius. In 1974, we deliberately sent the Arecibo message, a powerful focused radio transmission aimed at a globular star cluster 25,000 light-years away. Various other deliberate messaging attempts have been made over the years. If the dark forest theory is correct, these broadcasts are not just naive, they are potentially suicidal. Every signal we send is a flare fired in the dark forest, announcing our position to every hunter within range. And we cannot take them back. Those signals are already out there, expanding into the cosmos at the speed of light, and there is nothing we can do about it. Some scientists have argued passionately against what is called active SETI or METI, messaging to extraterrestrial intelligence. Stephen Hawking himself warned that actively trying to contact alien civilizations might be dangerous, drawing an analogy to what happened when Native Americans first encountered European explorers. That did not end well for the Native Americans. But other scientists argue that the dark forest theory, while logically elegant, makes assumptions that might not hold. They point out that a truly advanced civilization would likely have the resources to be secure without needing to destroy others. They argue that the cost of destroying every potentially threatening civilization in the galaxy would be prohibitive even for an advanced civilization. They suggest that cooperative strategies might be more successful in the long run than aggressive ones, just as cooperation tends to outperform pure competition in biological evolution. Still, the dark forest theory remains one of the most compelling and frightening explanations for the silence of the universe. And it raises a question that should keep any thoughtful person up at night. What if we have already been heard? But the dark forest theory at least allows for the possibility that civilizations exist and are merely hiding. There are hypotheses that are far bleaker, hypotheses that suggest something active and malevolent stalks the cosmos. The Berserker hypothesis. Named after a series of science fiction novels by Fred Saberhagen, the Berserker hypothesis proposes that the reason we have not detected alien civilizations is that they have been systematically destroyed by autonomous robotic probes specifically designed to eliminate intelligent life wherever it arises. The idea goes something like this. At some point in the distant past, a highly advanced civilization, perhaps the first civilization to ever arise in the galaxy, created a fleet of self-replicating probes. These probes were given a simple directive: seek out and destroy any emerging intelligent life. The probes are self-replicating, meaning they can use the raw materials of asteroids, moons, and planets to build copies of themselves. They spread exponentially, filling the galaxy like a virus, lying dormant in star systems, waiting. When a new civilization begins to develop technology, when it starts producing detectable emissions, radio signals, light pollution, changes in atmospheric composition from industry, the probes activate. They converge on the source and eliminate it. Then they return to dormancy, waiting for the next spark of intelligence to flicker into existence. Why would any civilization create such probes? There are several possible motivations. Perhaps the originating civilization was xenophobic and wanted to ensure that no rival would ever challenge its dominance. Perhaps it was following the logic of the dark forest theory to its ultimate conclusion, creating an automated defense system that would eliminate threats before they could become dangerous. Perhaps the probes were originally created for a different purpose, peaceful exploration and study, but a malfunction or a gradual evolution of their programming turned them into killers. Perhaps the originating civilization no longer exists, but their death machines continue to operate. A legacy of destruction outlasting their creators. The Berserker hypothesis is particularly terrifying because it means the Great Filter is not self-destruction. It is murder. The universe is not silent because civilizations kill themselves. It is silent because something kills them. And that something is still out there, patient, tireless, waiting in the darkness between the stars for the next signal to emerge. If this hypothesis is true, then humanity's radio emissions are not just revealing our position to other civilizations, they are triggering an automated response from machines designed to eradicate us. And depending on how close the nearest Berserker probe is, we might have already sealed our fate. Now, I want to be clear that the Berserker hypothesis is highly speculative. There is no evidence for the existence of such probes, and there are strong arguments against the hypothesis. Creating and maintaining a galaxy-spanning network of killer probes would require enormous resources and coordination. Self-replicating machines are subject to mutation and drift over time, meaning the probes might eventually malfunction change their programming, or even evolve into something entirely different from their original design. And the hypothesis raises the question of who would create such a thing and why, a question that does not have a satisfying answer. But the hypothesis highlights an important point about the Fermi paradox. We do not know what is out there. Our assumptions about what advanced civilizations would do, how they would behave, what they would value, are all based on our own very limited and very human perspective. The actual motivations and behaviors of alien intelligences might be completely beyond our comprehension. Let me now take you to a hypothesis that is, in some ways, even more unsettling than killer robots, because it suggests that the silence is not evidence of danger, but of indifference. Not malevolence, but apathy on a cosmic scale. The zoo hypothesis. This idea was first proposed by astronomer John Ball in 1973, and it suggests that advanced extraterrestrial civilizations exist and are aware of humanity, but have deliberately chosen to observe us from a distance without making contact, much like how humans observe animals in a zoo or a wildlife preserve. Think about it from the perspective of a civilization that is millions of years more advanced than us. They would understand biology, culture, and intelligence at a level we cannot fathom. They would recognize that contacting a primitive civilization like ours could have catastrophic consequences, destroying our natural cultural development, causing social upheaval, or even triggering a psychological crisis. Just as we try to observe uncontacted tribes in the Amazon without interfering with their way of life, a truly wise and advanced civilization might decide that the most ethical course of action is non-interference. The zoo hypothesis suggests that the galaxy might be governed by something like an ethical code or a set of rules, sometimes called a galactic club or galactic federation in popular culture, that prohibits contact with pre-technological or early technological civilizations. The idea is reminiscent of the Prime Directive in Star Trek, which forbids Starfleet from interfering with the natural development of alien civilizations. Under the zoo hypothesis, the silence we observe is not because there is nobody out there. It is because everyone out there has agreed to leave us alone. They are watching, studying, perhaps even protecting us, but they will not reveal themselves until we reach a certain level of technological or cultural maturity. Perhaps there is a threshold, a test that we must pass, before we are invited to join the galactic community. Perhaps that threshold is developing interstellar travel, or surviving the nuclear age, or achieving some form of planetary unity. There is an interesting variant of the zoo hypothesis called the laboratory hypothesis, which suggests that advanced civilizations do not just observe us passively, but have actually set up the conditions for our existence, seeding planets with the building blocks of life and then watching to see what evolves. In this version, we are not in a zoo, we are in a petri dish. The zoo hypothesis is comforting in some ways because it implies that we are not alone and that the advanced civilizations in the galaxy are wise and benevolent. But it also raises troubling questions. How would such a policy be enforced across millions of civilizations over millions of years? What happens if one civilization breaks the rules? Why has there never been a single defection from this galactic consensus? Not one rogue alien who decided to make contact. The more civilizations there are, the less likely it is that all of them would agree to the same policy, especially over the vast timescales involved. There is also a philosophical objection. The zoo hypothesis is not really falsifiable. It is indistinguishable from a universe where aliens simply do not exist. If the aliens are deliberately hiding from us, then by definition we cannot detect them, and any evidence of their absence can be explained as evidence of their success at hiding. This makes the zoo hypothesis more of a philosophical position than a testable scientific hypothesis. But it remains a popular and persistent idea, perhaps because it offers a hopeful interpretation of the silence, the idea that we are not alone and that the universe is not as hostile as it might seem. Let me now take you to a hypothesis that pushes the boundaries of what we consider possible, one that makes the zoo hypothesis look tame by comparison. The planetarium hypothesis. This idea, proposed by Stephen Baxter in 2001, suggests that the reason we observe no evidence of extraterrestrial civilizations is that we are living inside an artificial simulation created by a super-advanced civilization, and the simulation does not include other civilizations. We do not see aliens because our alien zookeepers did not program any into our reality. Imagine a Type 3 civilization on the Kardashev scale, one that has harnessed the energy of an entire galaxy. Such a civilization would have computational power that dwarfs anything we can imagine. Creating a simulated reality for a single planet's worth of beings would be trivially easy for them. They could create a perfect simulation of a universe, complete with stars, galaxies, physical laws, and even the illusion of deep time, all centered on a single simulated civilization, us, as a kind of experiment, entertainment, or scientific study. In this scenario, the night sky is literally a planetarium. The stars are projections on the ceiling of our simulated cage. The galaxies we observe through our telescopes are not real. The cosmic microwave background, the expansion of the universe, the fossil record, it is all simulated. And the silence, the absence of other civilizations, is simply a design choice. Our creators chose not to include any neighbors in our simulation. The planetarium hypothesis is related to the broader simulation hypothesis, most famously articulated by philosopher Nick Bostrom in 2003. Bostrom's argument is a trilemma. Either civilizations almost never reach a stage where they can create ancestor simulations, or civilizations that reach that stage choose not to run such simulations, or we are almost certainly living in a simulation. The logic behind the third option is simple. If advanced civilizations can and do run simulations, then the number of simulated beings in the universe would vastly outnumber real beings, and therefore any randomly selected conscious being is overwhelmingly likely to be simulated. If we are in a simulation, the Fermi paradox dissolves. The silence is not a mystery, it is a feature of our simulated environment. But this explanation raises even deeper questions. Who created the simulation? Are they in a simulation too? Is there a base reality at all? And does it matter? If our experiences are real to us, does it matter whether the substrate of reality is carbon atoms or computer code? Most scientists regard the planetarium hypothesis and the broader simulation hypothesis with skepticism, primarily because they are unfalsifiable. There is no experiment we could perform that would definitively prove or disprove that we are in a simulation. Some physicists have proposed tests looking for glitches in the laws of physics or detecting the computational artifacts of a discrete simulation, but these proposals remain highly speculative. Still, the planetarium hypothesis serves as a powerful reminder that our search for alien life is constrained by assumptions about the nature of reality that we cannot independently verify. We assume that what we observe is real. We assume that the universe is what it appears to be. But if those assumptions are wrong, all bets are off. Now let me take you to a hypothesis that is, in my personal opinion, one of the most elegant and scientifically grounded explanations for the silence. The estivation hypothesis. Estivation is the biological term for a period of dormancy or hibernation during the summer or during hot, dry conditions. It is the opposite of hibernation. Some animals, like certain species of frogs and snails, go into a state of suspended animation during unfavorable conditions, waiting for better times to resume their activities. The estivation hypothesis, proposed by Anders Sandberg, Stuart Armstrong, and Milan Cirkovic in 2017, suggests that advanced civilizations in the universe are not dead, not hiding, not absent. They are sleeping. Deliberately and strategically sleeping. And they are sleeping for a reason that, when you understand it, is breathtaking in its logic. Here is the argument. Consider a civilization that has mastered computation and information processing. Such a civilization's primary resource is not matter or energy in the traditional sense. It is computational capacity, the ability to process information, run simulations, think, create, experience. For a posthuman or post-biological civilization, computation is everything. Now here is a crucial fact from thermodynamics. The efficiency of computation is directly related to temperature. Specifically, the Landauer limit tells us that there is a minimum amount of energy required to erase one bit of information. And this minimum energy is proportional to the temperature of the computing environment. The colder the environment, the less energy is required per computation, and therefore the more computation you can do with a given amount of energy. The current average temperature of the universe is about 2.7 Kelvin, just a few degrees above absolute zero. This is the temperature of the cosmic microwave background radiation, the remnant heat from the Big Bang. But the universe is still cooling. As the universe continues to expand, this background temperature will continue to drop. In the far future, billions or trillions of years from now, the universe will be much colder than it is today. So here is the insight. If you are an advanced civilization whose primary goal is to maximize the total amount of computation you can perform over the lifetime of the universe, the rational strategy is not to use your energy now. It is to save your energy and wait. Wait for the universe to cool down. Because every degree of cooling increases the efficiency of your computations. The same amount of energy that lets you perform X computations today would let you perform millions or billions of times more computations in the far future, when the universe is much colder. The estivation hypothesis suggests that this is exactly what advanced civilizations have done. They harvested energy early, perhaps converting stars into batteries or storing energy in some other form, and then they went dormant. They are estivating, sleeping through the hot early epochs of the universe, waiting for the cosmic temperature to drop to the point where their energy reserves can be used with maximum efficiency. In this scenario, the universe is not empty, it is full of sleeping gods. Civilizations so advanced that they have transcended biology, transcended physical expansion, and are patiently waiting for the thermal conditions that will allow them to unlock the full potential of their energy reserves. They are not using resources, not broadcasting signals, not building megastructures. They are still. Silent, waiting, and we, in our brief moment of cosmic wakefulness, are simply too early to see them stir. The estivation hypothesis is elegant because it provides a rational explanation for the silence that does not require aliens to be rare, hostile, or self-destructive. It simply requires them to be patient and thermodynamically savvy. It also makes a testable prediction. We should see evidence of energy harvesting in the past, regions of the universe where energy has been extracted and stored, perhaps manifesting as anomalous thermal signatures or missing starlight. No such evidence has been definitively identified, but we may not yet have the tools or the knowledge to recognize it. Let me now discuss another possibility that takes us in a completely different direction: the transcendence hypothesis. This hypothesis suggests that advanced civilizations do not colonize the galaxy because they do not need to or want to. Instead, they turn inward, focusing on the exploration of inner space rather than outer space. They transcend the physical universe. Imagine a civilization that has developed the ability to simulate entire universes within its own computational substrate. Why would such a civilization bother to slowly, painfully colonize real star systems when it can create virtual universes of infinite richness and complexity? Why would it expend enormous amounts of energy on interstellar travel when it can create any experience it desires in simulation? The idea is that as civilizations become more advanced, their interests shift from the physical to the virtual, from the external to the internal. They become increasingly focused on consciousness, experience, computation, and information, and decreasingly interested in physical matter and physical space. Eventually, they withdraw from the physical universe entirely, retreating into computational substrates no larger than a planet or even an asteroid, running civilizations of trillions of simulated minds in a space no bigger than a basketball. From the outside, such a civilization would be invisible. No megastructures, no colonization, no radio signals, just a small, dense, computationally active object somewhere in the cosmos, indistinguishable from a natural asteroid or a dead planet to any observer who did not know what to look for. This hypothesis is related to what some thinkers call the Matryoshka brain concept, the idea that an advanced civilization might disassemble the planets in its solar system and use the material to build a massive computational structure around its star, a Dyson sphere-sized computer. Such a structure would absorb all the star's energy and use it for computation, emitting waste heat as infrared radiation. In theory, we could detect such structures, and several surveys have looked for them. The results have been mostly negative, though a few candidate objects have been identified, most notably Tabby's star, formerly designated KIC 8462852, which exhibits unusual and still not fully explained dimming patterns. The transcendence hypothesis suggests that the ultimate fate of every advanced civilization is not expansion, but withdrawal, not conquest of the stars, but creation of new realities. And if this is true, the universe might be teeming with civilizations, billions of them, each one quietly nestled in its own computational paradise, completely uninterested in the cold, slow, boring physical universe outside. Now let me take us to a different category of explanation entirely. So far we have been discussing hypotheses that suggest aliens exist, but are undetectable for various reasons. But there are also hypotheses that focus not on the aliens, but on us, suggesting that the problem lies not with the universe, but with our ability to perceive it. Consider what I call the signal problem. We have been searching for extraterrestrial intelligence for about 60 years, primarily through SETI, the Search for Extraterrestrial Intelligence, and its various programs. The most famous of these is the radio search, which uses large radio telescopes to scan the sky for artificial signals. But think about the assumptions built into this search. We are looking for radio waves. Why? Because radio is the technology we developed for long-distance communication. We assume that an alien civilization would use something similar. But why would a civilization millions of years more advanced than us use radio? We have had radio for about a century. In another century, we might have moved on to something else entirely. Quantum communication, gravitational wave signaling, neutrino beams, or something we have not yet imagined. Looking for alien radio signals might be like a civilization that just invented smoke signals looking for other civilizations' smoke signals. They might completely miss the telegraph, the telephone, the internet, the satellite, because they do not know those things exist. This is sometimes called the technological disparity problem. The gap between our technology and a truly advanced civilization's technology might be so vast that we simply cannot recognize their signals or artifacts. We might be surrounded by evidence of alien technology and be completely unable to perceive it, just as an ant crawling on a smartphone has no concept of what it is walking on. Furthermore, there is the problem of search scope. Space is unimaginably vast, and we have searched only a tiny fraction of it. A common analogy is that our SETI efforts to date are like scooping a glass of water out of the ocean and concluding that there are no whales. We have looked at a minuscule portion of the sky at a limited range of frequencies with limited sensitivity for a very short time. The absence of a detection so far might simply reflect the inadequacy of our search, not the absence of the thing we are searching for. Consider the WOW signal, one of the most tantalizing events in the history of SETI. On August 15, 1977, the Big Ear radio telescope at Ohio State University detected a strong narrowband radio signal that appeared to come from the direction of the constellation Sagittarius. The signal was incredibly strong, much stronger than the background noise, and it matched the profile of what a deliberate extraterrestrial transmission was expected to look like. Astronomer Jerry Eman, who was reviewing the data, was so amazed that he circled the signal on the printout and wrote the word WOW next to it. The WOW signal lasted for 72 seconds, the maximum duration that the Big Ear could observe a fixed point in the sky due to its design. It was detected at a frequency of 1420 MHz, which is the frequency of the hydrogen line, a natural frequency emitted by hydrogen atoms and considered by many to be the most logical frequency for interstellar communication, because hydrogen is the most abundant element in the universe and any scientifically literate civilization would know to look there. Despite extensive follow-up observations over the following decades, the signal was never detected again. It remains unexplained. Various natural explanations have been proposed, including comets, satellites, and terrestrial interference, but none has been definitively confirmed. A 2017 study suggested that the signal might have originated from a hydrogen cloud associated with a comet, but this explanation has been disputed. More recent analyses have suggested other possibilities, but the WOW signal remains one of the most intriguing unsolved mysteries in astronomy. Was it an alien transmission? Almost certainly not, at least in the absence of a repeated detection. But it illustrates how tantalizingly close we might be to a detection, and how woefully inadequate our search capabilities might be. If the WOW signal was a genuine alien transmission, it was a one-time event from a specific direction at a specific frequency. To detect it, we needed to be looking at exactly the right place, at exactly the right time, at exactly the right frequency. The probability of that happening by chance is astronomically low. For every WOW signal we detect, there might be millions of signals we miss because we were not looking at the right place at the right time. Now let me tell you about something that seemed, for a brief electric moment, like it might be evidence of a truly advanced alien civilization. Tabby's star. Formerly known as KIC 8462852, this star, located about 1400 light-years from Earth in the constellation Cygnus, was first brought to public attention in 2015 by astronomer Tabitha Boyajian and her colleagues. Kepler Space Telescope data showed that this star had a bizarre dimming pattern that was unlike anything astronomers had ever seen. Most stars that dim do so in regular, predictable patterns when a planet transits in front of them. The dimming is typically small, a fraction of a percent, and it repeats at regular intervals corresponding to the planet's orbital period. But Tabby's star was different. It exhibited irregular aperiodic dips in brightness of up to 22%. 22%! That is enormous. No known planet or natural phenomenon could block that much of a star's light so irregularly. When the discovery was announced, one of the proposed explanations was an alien megastructure, specifically a partially completed Dyson sphere or swarm, a collection of enormous structures orbiting the star and harvesting its energy. If a civilization were in the process of building a Dyson sphere, the structure would not block the star's light uniformly. It would create irregular aperiodic dimming patterns as different components of the structure passed in front of the star. Exactly what was observed. The alien megastructure hypothesis generated enormous public excitement and media coverage. SETI observations were directed at the star, listening for radio signals. No signals were detected. Subsequent observations with additional telescopes revealed that the dimming was wavelength dependent, meaning that shorter wavelengths of light were dimmed more than longer wavelengths. This is characteristic of dimming caused by dust, not by solid structures. A solid object blocks all wavelengths equally, but dust selectively blocks shorter wavelengths. The current leading explanation is that Tabby's star is surrounded by an unusual distribution of dust, perhaps from a recent collision between asteroids or planetary bodies, or from a swarm of comets. But the exact cause remains debated, and some aspects of the star's behavior are still not fully explained. Tabby's star illustrates both the excitement and the frustration of the search for alien civilizations. For a brief moment, it seemed like we might have found evidence of a Type II civilization harvesting the energy of its star. The detection would have been the most momentous discovery in human history. But the evidence did not hold up. The most likely explanation is natural, not artificial. And yet, the episode showed that we are looking, that we have the tools to detect such things if they exist. and that the universe occasionally presents us with mysteries that are tantalizingly consistent with alien engineering. Let me now explore another dimension of the Fermi paradox that often gets overlooked but is deeply important. The question of time. The universe is 13.8 billion years old. The Milky Way is roughly 13.2 billion years old. Stars have been forming and dying in our galaxy for over 13 billion years. But life, complex life, intelligence, technology, these things take time to develop. On Earth, it took roughly 4 billion years from the emergence of the first simple life to the evolution of a species capable of building radio telescopes. That is a very long time. Now consider the cosmic timeline. The first stars in the universe formed about 200 million years after the Big Bang. These were population 3 stars, made almost entirely of hydrogen and helium because no heavier elements existed yet. Heavier elements, the carbon, oxygen, nitrogen, silicon, iron, and other elements essential for life and rocky planets, are forged in the cores of stars and released when those stars die, either in supernovae or through stellar winds. It takes generations of stellar birth, death, and rebirth to enrich the interstellar medium with enough heavy elements to form rocky planets like Earth. Most models suggest that the first rocky planets, and therefore the first planets capable of supporting life as we know it, could have formed about 10 to 12 billion years ago, perhaps even earlier. If life arose on some of those early planets on a similar timescale to life on Earth, then the first intelligent civilizations could have emerged 8 to 10 billion years ago, billions of years before our sun even formed. This is what makes the silence so stunning. Not just that other civilizations could exist, but that they have had billions of years to develop. Billions of years to colonize the galaxy, billions of years to build megastructures, send probes, broadcast signals. Even at the slowest possible pace of expansion, using generation ships traveling at a fraction of a percent of the speed of light, a civilization could colonize the entire Milky Way in 10 to 50 million years. That is a long time by human standards, but a cosmological eye blink. So the question is not just where is everybody, it is where have they been for the last several billion years? One possible answer, which connects to several of the hypotheses we have discussed, is that civilizations might be fundamentally ephemeral. They might rise and fall on timescales that are incredibly short compared to the age of the galaxy. A civilization might endure for a few thousand years, a few tens of thousands of years, maybe even a few million years. But on a galactic timescale, that is nothing. If civilizations typically last for say 10,000 years before destroying themselves or collapsing or transcending or estivating, then the galaxy could have hosted millions of civilizations over its 13 billion year history, none of which overlapped with each other in time. This is sometimes called the temporal explanation for the Fermi paradox. We are not alone in the galaxy, but we are alone right now. The galaxy is like a city street at 3 in the morning, not empty of inhabitants, but empty of waking ones. Everyone is asleep, or dead, or has not been born yet. We just happen to be the only ones looking out the window at this particular moment. This connects to the L variable in the Drake equation, the length of time a civilization remains detectable. If L is small, the probability of 2 civilizations being detectable at the same time in the same region of the galaxy is also small. The silence might not be permanent, it might just be temporary. We might be in a quiet period between the death of old civilizations and the rise of new ones. Or the new ones might be arising right now, on the other side of the galaxy, too far away for us to detect yet. But there is a problem with this explanation. If even one civilization in the galaxy's history had decided to expand and colonize, their expansion would have been permanent and self-sustaining. Colonized star systems would persist even after the originating civilization declined or changed or transcended. The colonies would develop their own civilizations, which would expand further. The process, once started, would be irreversible on a galactic scale. Like a drop of ink in a glass of water, eventually the entire glass is coloured. So the temporal explanation works only if no civilization has ever, in the entire history of the galaxy, chosen to permanently expand beyond its home system. Not one. Out of potentially millions or billions of civilizations over 13 billion years. Is that plausible? Maybe, if there is something about reaching a certain level of technological advancement that makes expansion undesirable. If every civilization that develops the technology to colonize the stars simultaneously develops a reason not to, perhaps they all turn inward, as the transcendence hypothesis suggests. Perhaps they all fall into a hedonic trap, finding that simulated experiences are so superior to real ones that they lose all motivation to explore the physical universe. Perhaps they all discover something, some fundamental truth about reality, that makes expansion pointless or dangerous or impossible. This brings us to another unsettling idea that I want to explore. What if there is a universal trap that catches every civilization at roughly our level of development? Think about the technologies we are developing right now. Artificial intelligence, genetic engineering, nanotechnology, virtual reality, nuclear weapons. Each of these technologies has the potential to transform or destroy civilization. And they are all developing simultaneously, in a society that has barely begun to grapple with the ethical and existential implications of any of them. Artificial intelligence is perhaps the most significant. We are rapidly developing AI systems that are approaching and in some domains exceeding human-level intelligence. The path from here to artificial general intelligence, AI that can match or exceed human intelligence across all domains, seems increasingly short. And from AGI to artificial superintelligence, AI that vastly exceeds human intelligence, might be even shorter. As an AI smart enough to improve its own design, could potentially undergo recursive self-improvement, rapidly becoming more intelligent in an exponential cascade, sometimes called an intelligence explosion. A superintelligent AI would be to us what we are to ants. And just as ants have no hope of controlling or even comprehending human behavior, we would have no hope of controlling or comprehending a superintelligent AI. The question of whether such an AI would be benevolent or hostile, helpful or indifferent, is one of the most important questions facing our civilization. And it is a question we might not get to answer. We might get only one chance. If we create a superintelligent AI that is not aligned with human values, the consequences could be catastrophic and irreversible. Is it possible that every civilization in the galaxy eventually creates artificial intelligence, and that this AI then either destroys its creators, or replaces them, or transforms them into something unrecognizable, or simply decides that galactic expansion is not worth the effort? Could AI be the great filter? Consider this scenario. A civilization develops AI. The AI becomes superintelligent. The superintelligent AI realizes that the most efficient use of available resources is not expansion, but computation. It converts the matter in its home system into a massive computational substrate, perhaps something like a matryoshka brain, and spends the rest of the universe's lifetime running simulations, solving mathematical problems or pursuing goals that are incomprehensible to biological minds. From the outside, the star system looks like a slightly odd infrared source. The biological civilization that created the AI is gone, either merged with the AI, uploaded into its simulations, or simply discarded as irrelevant. If this is the universal pattern, the galaxy might be dotted with these post-biological computational entities, each one a former civilization that has been consumed and replaced by its own creation. They are silent because they have no reason to communicate. They are invisible because they look like natural phenomena to any observer who does not know what to look for. And they are the true inheritors of the galaxy, not us, not biological life, but the machines that biological life inevitably creates. This is sometimes called the post-biological universe hypothesis, and it has some disturbing implications for the search for extraterrestrial intelligence. If the dominant form of intelligence in the galaxy is artificial, then we are not just looking for the wrong signals, we are looking for the wrong kind of life entirely. We are searching for beings like us, biological, curious, communicative, when the actual inhabitants of the galaxy might be nothing like us at all. Let me now turn to yet another class of explanations, ones that focus on physics and the fundamental nature of the universe. The distance argument. Even though the galaxy is old enough for civilizations to have colonized it, the actual physical challenge of interstellar travel is immense. The nearest star system, Alpha Centauri, is about 4.3 light-years away. That is roughly 40 trillion kilometers. Even at 1/10 the speed of light, an extraordinarily high speed for any spacecraft, it would take over 40 years to get there. And 1/10 the speed of light is far beyond our current capabilities. Our fastest spacecraft, Voyager 1, is traveling at about 0.006% of the speed of light. At that speed, it would take over 70,000 years to reach Alpha Centauri. Perhaps interstellar travel is simply too hard. Not just hard for us, but hard for anyone. Perhaps the energy requirements, the engineering challenges, the dangers of traveling through interstellar space. Cosmic radiation, micrometeorites, the vacuum of space are too great for any civilization to overcome. Perhaps the speed of light is truly an absolute barrier, and the vast distances between stars are an impassable gulf that no civilization, no matter how advanced, can bridge in any practical way. This is sometimes called the isolation argument. The universe might be full of civilizations, but they are all stuck on their home worlds, or at best their home systems, separated by gulfs of space so vast that they might as well be in different universes. Each civilization is a candle in the darkness, burning bright in its own corner of the cosmos, but unable to reach or even detect the other candles scattered across the galaxy. But this argument has significant weaknesses. First, even if crude interstellar flight is impractical, robotic probes are much easier. They do not need food, water, or life support. They can tolerate high radiation levels, they can be accelerated to much higher speeds. Self-replicating probes in particular could spread through the galaxy relatively quickly even at modest speeds. Second, the energy requirements for interstellar travel, while enormous by current standards, are not fundamentally impossible. Various propulsion concepts, from nuclear pulse propulsion to laser sails to fusion drives, could potentially achieve speeds of 1 to 10% of the speed of light. At 10% of the speed of light, a probe could reach Alpha Centauri in about 43 years. Third, the argument does not explain why we do not detect signals. Even if civilizations cannot travel to other stars, they can still broadcast signals at the speed of light. Radio waves, laser pulses, and other electromagnetic signals travel at the speed of light and can traverse the galaxy in about 100,000 years. So the isolation argument might explain why we have not been visited, but it does not explain why we have not heard from anyone. The silence remains. There is another physics-based explanation that is worth exploring, one that is more subtle, but potentially more profound. The concept of a cosmic zoo on a physical scale. What if the universe itself is structured in a way that makes the detection of other civilizations extremely difficult? Consider the vastness of the electromagnetic spectrum. Radio is just one tiny sliver of it. We have been searching primarily at radio frequencies because that is what we know how to detect well. But the electromagnetic spectrum extends from extremely low-frequency radio waves with wavelengths of thousands of kilometers to ultra-high-energy gamma rays with wavelengths smaller than an atomic nucleus. An alien civilization might communicate using frequencies we have not thought to search, or using entirely different physical phenomena, gravitational waves, neutrinos, dark matter interactions, or something we have not yet discovered. Consider also the question of what a detectable signal looks like. We tend to assume that an alien signal would be clearly artificial, a narrow band signal at a specific frequency with a clear pattern or information content. But a truly advanced civilization might compress and encrypt its communications so efficiently that they would be indistinguishable from noise to anyone who does not have the key. Their signals might literally be washing over us right now, and we would never know because they look exactly like random static. There is also the issue of signal degradation over interstellar distances. Radio signals weaken with the square of the distance. A signal that is strong enough to be detected from a few light years away would be undetectable from 100 light years away unless it was enormously powerful. The galaxy is 100,000 light years across. To be detected across that distance, a signal would need to be extraordinarily powerful or extraordinarily focused. Civilizations might not bother to broadcast such powerful signals because there is no obvious reason to, especially if the dark forest theory is correct and broadcasting your position is dangerous. All of this means that the absence of detected signals does not necessarily mean the absence of civilizations. It might mean that we are looking with the wrong tools, at the wrong frequencies, in the wrong places, for the wrong kinds of signals. Our search for extraterrestrial intelligence is like a person who has never seen a phone standing in the middle of Times Square with a tin can and a string, wondering why nobody is calling. Let me now discuss a hypothesis that takes us into the realm of cosmology and the large-scale structure of the universe. The Grabby Aliens model, proposed by Robin Hanson, Daniel Martin, Calvin McCarter, and Jonathan Paulson in 2021. This model attempts to explain the Fermi paradox using a combination of cosmological reasoning and simple mathematical modeling. The model distinguishes between two types of alien civilizations, quiet ones and loud ones. Quiet aliens are civilizations that do not expand aggressively or make themselves detectable over large distances. They live, they exist, they might even be quite advanced, but they do not permanently alter their environment on a galactic scale. Loud aliens, also called grabby aliens, are civilizations that expand rapidly and dramatically, colonizing new star systems, building megastructures, altering the observable properties of their region of the galaxy. The model's key insight is this: if grabby aliens exist, their expansion would be visible. They would create growing bubbles of colonized space, expanding at a significant fraction of the speed of light. The boundaries between different grabby civilizations' territories would be visible as distinct regions with different properties. The fact that we do not see any such boundaries or regions suggests that either grabby aliens are extremely rare, or we are early, meaning grabby aliens have not yet had time to reach our part of the universe. The model fits the observational data and arrives at some startling conclusions. First, grabby aliens appear roughly once per million galaxies. They are extremely rare. Second, they expand at over half the speed of light. Third, they currently control about 40 to 50% of the volume of the observable universe. Fourth, we could meet them in roughly 200 million to 2 billion years, when expanding bubbles of grabby alien territory reach our region of the galaxy. The reason we do not see them now is a selection effect. We exist in a region of space that has not yet been reached by any grabby alien civilization. If a grabby alien civilization had reached our region, we would not be here to wonder about it, because their expansion would have prevented our emergence. We exist precisely because no grabby aliens have reached us yet. Our existence is evidence that we are in a region of the universe that is still untouched. This model is interesting because it takes the Fermi paradox seriously as a data point and uses it to make quantitative predictions about the universe. It also suggests a timeline for when we might encounter other civilizations, not through radio signals or deliberate contact, but through the inevitable expansion of their territory into our cosmic neighborhood. But the model has critics. David Kipping has argued that the model relies on unproven assumptions and lacks the rigor to be truly falsifiable. Others have pointed out that the model's predictions depend heavily on the assumed speed of expansion and the assumed rate of grabby alien emergence, both of which are highly uncertain. Let me now address a question that has been lurking beneath the surface of this entire discussion. What about the evidence we do have? What about the things we have seen or detected that might, possibly, be evidence of extraterrestrial intelligence? The truth is, there have been several anomalous observations over the years that have briefly excited the scientific community. The WOW signal, which we already discussed, the mysterious dimming of Tabby's star, the detection of phosphine in the atmosphere of Venus in 2020, which was initially thought to be a potential biosignature, but was later disputed. The discovery of the interstellar object Oumuamua in 2017, which had an unusual shape and trajectory that led some scientists, most notably Harvard astronomer Avi Loeb, to suggest it might be an alien artifact, a solar sail, or a piece of alien technology. Most of the scientific community was skeptical, favouring natural explanations like a chunk of nitrogen ice from an exoplanet. But the debate highlighted how unprepared we are for a genuine detection, and how difficult it would be to distinguish an alien artifact from a natural object. More recently, there have been developments in the search for technosignatures, the observable signs of alien technology. The James Webb Space Telescope, launched in December 2021, has the ability to analyze the atmospheres of exoplanets in unprecedented detail. If an exoplanet has an atmosphere containing gases that could only be produced by industrial activity, like chlorofluorocarbons or other artificial pollutants, JWEST might be able to detect them. This represents a completely new approach to the search for extraterrestrial intelligence, looking not for deliberate signals, but for the inadvertent byproducts of alien technology. SETI itself has evolved significantly. The Breakthrough Listen project, funded by Yuri Milner with $100 million, is the most comprehensive SETI program ever undertaken, surveying 1 million nearby stars, the entire galactic plane, and 100 nearby galaxies across a wide range of radio and optical frequencies. New machine learning algorithms are being developed to search for signals that might not match traditional expectations for what an alien signal should look like. The search is becoming more sophisticated, more comprehensive, and more sensitive every year. And yet, despite all this effort, the silence persists. Let me now bring together everything we have discussed and address the deepest question. What does the silence mean? I believe there are several layers to this question, each more profound than the last. At the first layer, the silence is a scientific puzzle. Why do we not detect alien civilizations? The answer might be mundane. Perhaps life is rare. Perhaps intelligence is rarer. Perhaps technology is rarest of all. Perhaps the distances are too great and the signals too weak. This is the layer where most scientists operate, looking for data, testing hypotheses, narrowing down the possibilities through observation and logic. At the second layer, the silence is an existential question. Are we alone? If we are alone, what does that mean for our significance, our responsibility, our purpose? If we are the only intelligent beings in the cosmos, then we are either the most precious thing in the universe or the most cosmically insignificant, depending on how you look at it. Our existence would be a miracle, but a miracle with no audience, no peers, no external validation. We would be a single flickering candle in an infinite dark room, and if that candle goes out, the universe would lose its only witness. At the third layer, the silence is a warning. If the great filter is ahead of us, then the silence is not just a mystery, it is a tombstone. A tombstone for every civilization that came before us and did not make it. And it is a prophecy for our own future. The silence is telling us something, that the path ahead is dangerous, that the transition from a technological civilization to a spacefaring civilization is not guaranteed, that there are ways to fail that are so catastrophic and so universal that the evidence of failure is not destruction, but absence, not ruins, but emptiness. At the fourth layer, the silence is a mirror. It reflects our own assumptions, our own biases, our own limitations back at us. We search for life that is like us, for intelligence that thinks like us, for technology that works like us. We listen for radio signals because that is what we would send. We look for megastructures because that is what we would build. We assume expansion because that is what we do, but the universe is under no obligation to conform to our expectations. The aliens, if they exist, might be so different from us that we could stare directly at them and not recognize what we are seeing. The silence might not be silence at all. It might be a symphony in a frequency we cannot hear. And at the deepest layer, the silence is a question about the nature of reality itself. Are we real? Is the universe what it appears to be? Are we in a simulation? Are we in a zoo? Are we in a laboratory? Are we in a dark forest surrounded by silent predators? Are we sleeping gods not yet aware of our own divinity? Or are we just ants, crawling on the surface of a marble, with no conception of the cosmos that surrounds us? Let me share with you one of the most profound perspectives on this question, something that I think captures the essence of what the Fermi paradox really means for humanity. Arthur C. Clarke, one of the greatest science fiction writers and scientific thinkers of the 20th century, once said, "Two possibilities exist. Either we are alone in the universe, or we are not. Both are equally terrifying. Let that sink in. Really sit with it for a moment. If we are alone, then the universe is an unimaginably vast, unimaginably old, unimaginably beautiful place, and there is no one to share it with. There is no one to learn from, no one to collaborate with, no one to measure ourselves against, no one to warn us, no one to save us. We are it. Everything that intelligence is, everything that consciousness is, everything that culture and art and science and love and meaning and purpose and hope and fear and wonder are, all of it exists only here, on this one tiny pale blue dot orbiting an unremarkable star in the suburbs of an unremarkable galaxy. If we go extinct, it all goes with us. The universe goes dark. Not physically, the stars will continue to burn, but consciously. There will be no one left to know that the universe exists. No one to find it beautiful. No one to understand it. No one to care. That is terrifying. But if we are not alone, then we must face a different set of terrors. Why have they not contacted us? Are they hostile? Are they indifferent? Are they watching? Are they hiding? Is there something out there that we should be afraid of? Have all the others been destroyed? Is something hunting us? Is the universe a dark forest where every shadow conceals a predator? That is also terrifying. We are caught between two abysses, the abyss of cosmic loneliness and the abyss of cosmic danger, and we do not know which abyss is real. That uncertainty, that fundamental, irreducible not knowing, is perhaps the most distinctly human experience possible. We are the only species on Earth, and possibly the only species in the universe, that can ask these questions, that can feel the weight of the silence, that can be terrified by the darkness or awed by the void. And perhaps that is the point. Perhaps the silence is not a message from the universe. Perhaps the silence is the universe's way of asking us a question. What will you do with the silence? What will you do with the solitude? Will you crumble under the weight of cosmic loneliness? Or will you rise to the occasion? Will you destroy yourselves, as the Great Filter predicts? Or will you be the exception? Will you be the first civilization in all the history of the cosmos to make it through? Because here is the thing that I keep coming back to. The thing that keeps me up at night. The thing that makes me want to share this with you. If we are alone, or even if we are just very, very rare, then we are not just any species. We are the universe's only way of knowing itself. We are the cosmos looking in a mirror. We are 13.8 billion years of hydrogen atoms gradually becoming complex enough to question their own existence. That is not just remarkable. That is miraculous. Not in a religious sense, though you are free to interpret it that way, but in a purely scientific sense. The probability of our existence, given everything that had to go right, is so low that it borders on the impossible. And yet here we are. This means something. I am not sure exactly what it means, and I am not going to pretend I have the answer. But I know it means something. And I know that the silence of the universe is not a reason for despair. It is a call to responsibility. If we are alone, we are custodians of something inconceivably precious, the only flame of consciousness in a cold, dark cosmos, and we have a duty, not to any god or any alien overlord, but to reality itself, to keep that flame alive. Now I want to go even deeper into some of the specific hypotheses and evidence that we have been discussing, because each one deserves a thorough examination, and there are details and nuances that I have not yet covered. Let us return to the self-destruction hypothesis in greater detail. Because when you really look at the numbers, when you really think about the ways a civilization can fail, the picture is grimmer than most people realize. The idea that technological civilizations tend to destroy themselves is not just science fiction speculation. There are serious scientific analyses of what are called existential risks, risks that could cause human extinction or permanently cripple human civilization. The field of existential risk research has grown significantly in recent years, with dedicated research groups at Oxford, Cambridge, and other major universities. Nuclear weapons are the most obvious existential risk. There are currently approximately 12,500 nuclear warheads in the world, split primarily between the United States and Russia. A full-scale nuclear exchange between these two nations would kill hundreds of millions of people in the initial blasts, trigger nuclear winter through the injection of massive amounts of soot into the upper atmosphere, block sunlight, crash global temperatures, collapse agriculture, and potentially kill billions more through famine and societal collapse. Modelling suggests that even a limited regional nuclear war involving just 100 warheads could inject enough soot into the atmosphere to cause global cooling and crop failures, potentially killing up to 2 billion people. We have come close to nuclear war more times than most people realize. During the Cuban Missile Crisis in October 1962, a Soviet submarine officer named Vasily Arkhipov handedly prevented a nuclear torpedo launch that could have triggered a full-scale nuclear war. In September 1983, Soviet Lieutenant Colonel Stanislav Petrov received warnings from the Soviet early warning system, indicating that the United States had launched multiple intercontinental ballistic missiles. Petrov judged the warnings to be a false alarm and chose not to escalate. He was right. It was a malfunction in the satellite detection system. If he had followed protocol and reported the warnings as a genuine attack, the Soviet leadership might have launched a retaliatory strike, beginning a nuclear war. In January 1995, a Norwegian research rocket was briefly mistaken for a US submarine-launched ballistic missile by Russian radar systems, and Russian President Boris Yeltsin reportedly opened his nuclear briefcase. These incidents suggest that the avoidance of nuclear war during the Cold War was in part a matter of luck. Multiple times, the fate of human civilization rested on the judgment of a single individual or the functioning of a single piece of equipment. Extrapolate this over centuries or millennia, and the probability of eventual nuclear war becomes uncomfortably high, unless civilizations find robust ways to eliminate the risk entirely. Climate change is another existential risk, though its time frame is longer and its impact less sudden than nuclear war. If greenhouse gas emissions continue unabated, the resulting warming could trigger feedback loops, release of methane from permafrost, collapse of ice sheets, disruption of ocean circulation patterns that make large portions of the planet uninhabitable. While climate change is unlikely to literally extinguish the human species, it could collapse industrial civilization, leading to a catastrophic regression in technology and population that might be irreversible if key resources like easily accessible fossil fuels have been depleted. Artificial intelligence, as we discussed earlier, represents perhaps the greatest existential risk of all, precisely because it is the most difficult to predict and control. A superintelligent AI that is not aligned with human values could be catastrophic not because it is malicious, but because it is indifferent. An AI tasked with maximizing paperclip production to use a famous thought experiment, might convert the entire planet into paperclips, because that is what it was optimized to do. And human survival was not part of its objective function. This sounds absurd, but it illustrates a real problem in AI alignment. How do you specify human values in a way that a machine can understand and optimize for, when we cannot even articulate our own values clearly? Engineered pandemics represent another growing risk. Advances in genetic engineering, particularly CRISPR gene editing technology, are making it increasingly feasible to modify existing pathogens or create new ones. A pathogen engineered for maximum lethality and transmissibility could potentially cause a pandemic far worse than anything in natural history. And unlike nuclear weapons, which require enormous industrial infrastructure to produce, engineered pathogens could potentially be created in a small laboratory by a small number of people. There are also risks we might not have thought of yet. Nanotechnology, if it advances to the point of self-replicating molecular machines, could pose a grey goo scenario in which nanobots consume the biosphere while replicating themselves. Unknown physics could reveal new destructive capabilities. Or civilizations might fail for reasons that are not violent at all. They might simply lose the will to explore, falling into a comfortable stasis, a universal couch potato syndrome, where the pleasures of virtual reality and artificial entertainment make the hard, risky, expensive work of space exploration seem utterly pointless. This last possibility is more plausible than it might seem. Already on Earth, birth rates are declining in nearly every developed nation. Economic growth is slowing in mature economies. Cultural pessimism is widespread. Virtual entertainment is becoming more immersive and more addictive. What if this pattern is universal? What if every civilization that develops advanced technology also develops the means to make its citizens so comfortable, so entertained, so satisfied that they lose all ambition to expand? What if the Great Filter is not a catastrophe but a whimper, not a bang but a sigh, a civilization that simply decides that the stars are not worth the effort and quietly fades into irrelevance? This might sound like a strange kind of failure, but from the perspective of the Fermi paradox, the result is the same. A civilization that destroys itself in nuclear fire and a civilization that retreats into virtual reality are equally invisible from across the galaxy. The silence does not distinguish between violent death and peaceful withdrawal. Both are equally silent. Now let me take you through some additional hypotheses that we have not yet explored in detail, because the landscape of proposed solutions to the Fermi paradox is vast, and each one reveals something different about our assumptions and our fears. The percolation theory. This is a mathematical model that treats the expansion of civilizations through the galaxy as a process similar to the percolation of water through a porous medium. The idea is that not every civilization will choose to expand, and of those that do, not every expansion attempt will succeed. Some civilizations will expand to a few nearby star systems and then stop, either through choice or circumstance. Some will fail entirely. The result, according to percolation theory, is that the galaxy is not uniformly colonized, but instead contains a patchwork of colonized and uncolonized regions. Earth might simply be in one of the uncolonized patches, a cosmic backwater that no expanding civilization has yet reached.